I will be presenting our paper IronMask, which is a new versatile verification tool for masking security. In this work, we reason about the security of implementations against side-channel attacks. These attacks derive information about the secret values manipulated during the execution of an encryption algorithm from measurements such as power consumption or electromagnetic radiations. And so the most deployed countermeasure against this class of attacks is the masking schemes. The idea is to split a sensitive variable into n values that we call shares, and their recombination should give the original secret. Typically, the first n-1 shares are drawn uniformly at random, and the last share is the recombination of the secret and the previously generated shares. This helps break the dependence of the secret with any set of n-1 shares, making it difficult to recover the secret as n grows. To reason about the security of masking schemes, the community introduced the idea of leakage models. Usually, we prove that a computational circuit is secure in a certain model if the leaking variables do not reveal any information about the secret values. So the most widely used model until now is the probing model, where we consider that during an execution, there is a fixed number of T leaking variables. Another widely used model is the random probing model, where each variable leaks with a certain probability p, independently from the others. And the last one is the noisy leakage model, where all variables leak a noisy function of their value. So in any model, the security of almost all masking approaches relies on the security of small gadgets and their composition. So a gadget is just a masked circuit which performs a certain operation on masked variables, such as addition or multiplication. And even at reasonable orders, masking orders, the manual verification of security properties on small gadgets has been shown to be very error prone. Therefore, automatic tools are regularly built to apply a formal verification method. The goal behind automatic tools is to check security and composition properties for relatively small circuits and gadgets. The main idea is to determine the sets of variables during the execution of an algorithm, which can potentially reveal information on the secret inputs, and then, depending on the checked property, conclude on the security of the considered circuit. Our contributions can be summarized as follows. We formalize all of the probing and random probing properties of the state-of-the-art from a single common building block function and show that all of the security properties can be verified using a unique instantiation of this function. From this formalization, we provide an exact verification method for almost all circuits and gadgets in the state-of-the-art using an extension of the algebraic characterization introduced in previous works of gadgets with linear randomness, which means where all random values are additive, to more general gadgets with nonlinear randomness. In fact, many previous tools in the state-of-the-art perform verification, but provide sometimes inexact results. This means that they can deem a circuit insecure while it is actually secure. With our strategy, we eliminate this case from the verification. And finally, we introduce IronMask, a new versatile verification tool for all probing and random probing-like properties in the state-of-the-art. IronMask supports the verification of traditional gadgets with linear randomness, as well as newly formalized gadgets with nonlinear randomness, and it provides a complete verification method for both types of gadgets based on our extended algebraic characterization. IronMask also implements several optimizations to make the verification faster. So we will first start by taking a look at the building block for the formalization of security properties. So security proofs generally demonstrate that the observations made on a masked circuit can be perfectly simulated from a subset of its input shares. A perfect simulation basically means that um, an algorithm with access to these input shares can produce a perfect simulation of the distribution of the observed variables. If the number of shares needed for such a simulation is less than the total number of shares, then we can conclude that the observations don't reveal information about the actual secret, because to reveal information about it, we need all of the shares to be involved in the computation. So the idea of the formalization is that given a set of probes on a circuit and potentially a set of output shares probes, we need to determine the set of input shares necessary for perfect simulation of P and O. For instance, if we take the following set of variables where R0 and R1 are values drawn uniformly at random, and A is our input sharing, we can observe that only the share A2 is needed for a perfect simulation of the distribution of this set. Why is this the case? It's simply because the distribution of the first two variables is made uniform thanks to the addition of the respective random values R0 and R1. So this technique is common to the verification of any security property in the state of the art. To formalize it, we define a single building block SIS function for sets of input shares. This function takes as input a set of probes on internal variables of the gadget, as well as a set of output shares, and returns a set of input shares necessary and sufficient to perfectly simulate all of the considered probes. Regardless of the strategy this function implements, if it respects the described signature, we show in our paper that it can be used to express all of the security properties. In the following, I will present an instantiation of this function, which leads to an exact verification method for some forms of gadgets. We first start with the algebraic characterization of gadgets with linear randomness. For this kind of gadgets, we consider that input shares go through an arithmetic circuit F, which can perform any operations such as addition and multiplication. Then, the random values used by the gadget only appear in the second arithmetic circuit R, which takes as input the vector of randomness small r and the output of the circuit F. So each coordinate in the vector R is basically drawn uniformly at random. The linear arithmetic circuit is only allowed to perform linear operations between the output of F and the random values, which means that the random values are additive on all variables involved in the gadget. Thanks to this structure, any internal variable on such a gadget can be expressed as the sum of the output of an arithmetic function f of p, which takes the input sharings as input, with a linear combination of some random values from the vector R. This linear combination is expressed through the vector of coefficients S of p. So given a tuple of probes, P1 through PD, on the gadget, we are interested in determining the set of input shares necessary for a perfect simulation of all probes in P. To do this, we need to first determine the probes which are distributed uniformly at random thanks to addition of random values. So thanks to the particular form of the probes in this case, we can easily determine this using a Gaussian elimination technique. In other words, we can construct a matrix S where the ith row is the vector S of P of the randomness dependence for the corresponding probe I. Then we can perform a row reduction on this matrix to obtain a matrix of the following form, as you can see, where the first m rows are equal to 0, and the remaining rows each contain a non-zero coefficient at a column which does not appear at any other row. This is observed through the structure of the identity submatrix. Thanks to the properties of the row reduction, we can apply the same set of operations on the original vector of probes using the invertible matrix N. We can see, thanks to the form of the matrix S prime, that the first expressions P prime 1 to P prime M do not involve any random values, while the remaining expressions each contain a unique random value which does not appear anywhere else. This means that the expressions of P prime M plus 1 to P prime D can be simulated uniformly at random, and the input shares necessary for the perfect simulation are exactly the ones appearing in the expressions of P prime 1 to P prime M. We prove in our paper that perfectly simulating the P prime I probes is equivalent to perfectly simulating the PI probes. Finally, thanks to the exactness of the Gaussian elimination technique, we are sure that the determined input shares are necessary and sufficient for a perfect simulation, making the verification method exact. And this is typically the instantiation of SIS function, which is implemented in IronMask for gadgets with linear randomness. We can extend this algebraic characterization to more general gadgets where random values are not always additive. Here we take the example of two input gadgets. we consider that before performing any operations between input shares, some random values are added to their expressions. In other words, each of the input shares of x1 and x2 go through linear arithmetic circuits R1 and R2, along with the corresponding randomness vectors small r1 and small r2. Then, the outputs of R1 and R2 are given as input to the general arithmetic circuit F, which can perform any operations before finally adding some random values to its output thanks to the linear arithmetic circuit R. So basically, the circuits R, R1, and R2 are only allowed to perform additions, while F can perform any operations. This covers newly constructed gadgets, for instance, in the state of the art, such as multiplication gadgets, which first refresh their input sharings with new random values. The only assumption we need in this case is that the random values in the three randomness vectors are all independent and drawn uniformly at random. And this description can be extended to gadgets with more input sharings. In this case, on such gadgets, the expression of any probe is a bit more complicated since we need to consider all arithmetic circuits. Nevertheless, we can still express any probe as a sum of a linear combination of randomness from vector R and the output of an arithmetic function f of p. Then, the inputs of this function f of p are also expressed as sums between input shares and random values thanks to the structure of the circuits R1 and R2. We can extend the verification technique we described for gadgets with linear randomness to this kind of gadgets by performing additional operations. In other words, we need to perform three Gaussian eliminations. The first one with respect to random values in the vector small r. This can be done as before with the same construction for the matrix S. Then, from the resulting expression, we can do some kind of a factorization on the expressions, which we detail in our paper, in order to perform two additional Gaussian eliminations, one with respect to random values appearing in R1 and one with respect to random values appearing in R2, to eliminate any random values appearing in the remaining expressions. At the end, some expressions will be distributed uniformly at random thanks to the randoms from R. Some will be distributed uniformly at random thanks to the randoms from R1 and R2, and the input shares necessary to perfectly simulate the remaining probes are exactly the ones appearing in the remaining expressions. In our paper, we prove that this strategy is an exact verification method for such gadgets. So IronMask is a new tool that we developed to check probing and random probing security properties using the algorithms presented earlier. It is written completely in C and implements state-of-the-art verification optimizations to further accelerate the verification. It also represents variable dependence as integer arrays to accelerate operations using simple XORs and ANDs. To give you an overview, you can give the tool as input any gadget represented as in this example. The first lines describe the configuration with input and output variables, random variables, and the number of shares. Then the remaining lines are simply the computations done by the gadget. Given to IronMask, it can check probing-like properties such as SNI or NI or PINI, and either deem the circuit secure or provide a counterexample as described by the properties. In the case of random probing-like properties, it computes the corresponding failure function FFP, which we recall in our paper. For instance, to verify SNI, you give the tool the name of the file of the circuit, the property name, and the parameter for the property of any, in this case, the T parameter. To evaluate IronMask, you can see in this table a comparison between most important tools in the state of the art in terms of support for different forms of gadgets, as well as the efficiency of the verification. Some verification tools, as you see, support gadgets but do not provide exact results in a general case. While IronMask does not handle gadgets with more than two inputs for nonlinear randomness, it provides an exact verification method for all gadgets with linear randomness and nonlinear randomness with two inputs, which is not supported by any other tool. Compared to VRAPS, the only other tool which we could compare to check random probing-like properties, IronMask provides fast verification, while VRAPS uses symbolic computations and is much slower. In terms of performance, IronMask is competitive and has similar performance to other fast verification tools for probing-like properties, and we provide full benchmark and analysis in our paper for this. In the case of random probing-like properties, IronMask has a clear speedup compared to wraps. We take the example of the well-known ISW multiplication circuit for 5, 6, and 7 shares configurations. We can see through the increasing number of shares that verification with IronMask scales well with the number of shares, while wraps quickly becomes impractical to use. To conclude, in this work, we introduce a new formalization of all probing and random probing-like properties. Then, using an extension of an algebraic characterization introduced in previous works, we provide exact verification methods which covers all gadgets used in the state of the art. From this theory, we derive a new formal verification tool, IronMask, which is competitive with other verification tools for probing-like properties. And for random probing-like properties, our tool is several orders of magnitudes faster than the previous tool wraps, besides providing an exact method, which is not the case for wraps. And for future works, we would like to extend IronMask to support any finite field and any gadgets without being limited to gadgets with two inputs in the case of nonlinear randomness. Thank you all for your attention.